Okay, good morning. We are going to be on page 46. Last week, all the stuff that we did with vapor pressure was just sort of like, what is vapor pressure and all that. It's not going to be tested. Okay, so we're starting to get into the stuff that will be, which is stuff relating to intermolecular forces, because AP loves intermolecular forces. So we're going to be comparing here three compounds, propanone, and if you're like into your organic chemistry, you'll notice that that has 3 carbons, hence the prefix prop. Okay, we have ethanol, which has 2 carbons, hence the prefix F. And let's just take a quick look at these compounds here. What type of intermolecular forces will we find between propanone molecules? What type of intermolecular forces will we find between propanone molecules? It's okay if you don't remember. Dipole, dipole, yes, because we have that oxygen. And why is that arrow pointing towards oxygen? Yeah, because the oxygen is very electronegative. What does it mean to be very electronegative? Yeah, they pull bonding electrons towards themselves. So O is very electronegative, pulls bonding electrons to itself. Okay, and that means that the oxygen is going to be slightly, and if you remember how to draw the little Greek lowercase delta, the oxygen will be slightly positive or negative? Negative. And that means that the carbon here will be slightly positive. All right, where did I put? There we go. We're on page 46. I'll just give you this for now. I'll get you the rest of the passes workbook so we can kind of here. Okay. So we have a dipole, and don't forget how to draw a dipole arrow. You draw the arrow with a little cross at the positive end. All right, so we have dipole-dipole forces. Are there any other intermolecular forces in between propanone molecules? In between propanone. Now, in order to have hydrogen bonding, what does the hydrogen have to be like actually bonded to within the molecule? Ooh. To have hydrogen bonding, H must be covalently bonded to who? Nitrogen or oxygen or fluorine. And why those 3? Because those 3 are the most electronegative elements. And what they will do is they will pull the electron density away from the hydrogen, leaving, remember hydrogen, it just has its 1 proton and it has 1 electron that is being shared. Let's say it's with oxygen. Okay, say oxygen is over here. and here's our hydrogen with its 1 proton, and we have these 2 electrons bonding in between, and the oxygen is pulling those bonding electrons towards itself, leaving us with a virtually naked proton. Yes, which means that we can get, and because it is so small, the other particles can get really close to it. So if we have the hydrogen here, because the hydrogen is so small, you know, another oxygen molecule could get really close to it. Does that make sense? Okay, and so that nearness of the negative charge and the positive charge will also make the bond, the hydrogen bond, stronger. Okay, so do we have the ability to hydrogen bond in propanone? No, because the oxygen is, or sorry, the hydrogen is not bonded to oxygen, so there's no hydrogen bonding. Is there any other type of intermolecular force between propanone molecules? I can't hear you, but I think you're saying the right thing. Yes, all molecules have London dispersion forces. Okay, so we have London dispersion forces. Which kind of force is going to be the most important in determining the properties of propanone? Is it going to be those dipole-dipole forces or those London dispersion forces? Dipole-dipole. Okay, so those are the most important. Yeah. What were the London dispersion forces? Okay, so London dispersion forces are caused by the temporary motion of atoms. Let's see, do we have IMFs here? IMFs. Uh-huh. What do I even have in here? This doesn't look very promising. Oh, here we go, temporary dipole. Oh, yes, here we go. London dispersion forces. So we have the electrons temporarily move to one side of the atom or molecule, okay, just because of random motion. Yes? We now have a slightly negative end and a slightly positive end, temporarily. That's why it's a temporary dipole. Okay, and what will happen is that temporary dipole will be next to, say, another neutral molecule, and this positive charge here will then pull on the electrons in the other one. Okay, and we can see that happening here. We get the electrons, they're moving, all moving this way, moving more this way, and so we now end up with another temporary dipole. This one is called an induced dipole because these electrons move in response to the original temporary dipole here. Okay, so this one happens by random chance. This one over here, this dipole, happens by being induced by the other dipole. Okay, and now we have a positive end beside a negative end, and those two will attract each other, and that right there, the force between temporary dipoles, is the London dispersion forces. And so it happens in polar molecules, it happens in non-polar molecules. Any type of molecule, you'll always get these London dispersion forces. But if you have dipole-dipole forces present, most of the time they will be the most important force. It's only if you get something really, really huge with lots of electrons that perhaps the London dispersion forces will be more important than a dipole-dipole force. Okay. All right. Okay, so that was propanone. And then we have ethanol. Let's consider ethanol. What are the intermolecular forces in ethanol, between ethanol molecules? we will get hydrogen bonding because we have the hydrogen is bonded to a very electronegative oxygen, okay? And you can see the dipole moment is pointing towards the oxygen. It's the combination of this bond dipole here and this bond dipole here. You can see the net of those two is in that direction, okay? So we do have hydrogen bonding. What else do we have? We have London dispersion forces, LDFs, London dispersion forces. And whenever you have hydrogen bonding, you can also say you have dipole-dipole, but whatever. Which of those is going to be most important? Which is going to affect it the most because it is the strongest? You look like you want to say something. It's 1. Yes, I didn't know. I thought you were like thinking and going, I didn't know you were saying number 1, but yes, number 1. Okay, so the hydrogen bonding, because hydrogen bonding are the strongest of the intermolecular forces, that's going to be it. So if we're comparing propanone and ethanol, which one has stronger intermolecular forces? Ethanol has stronger intermolecular forces than propanone. Now let's consider water. What kind of forces do we have in water? We have hydrogen bonding, because we have that H attached to the O. We have, anytime we have hydrogen bonding, we also have dipole-dipole, although they're almost irrelevant because of the hydrogen bonding. And we have London dispersion forces, because we always have London dispersion forces. Which of those is the most important for water? Hydrogen bonding. It is the strongest of them all. All right, now, out of ethanol and water, whose forces are going to be stronger and why? And the 3 sheets are over there, okay? Just right there, yeah. Water. Water is going to be stronger. Why is that? Sorry? It doesn't have slackers. You're absolutely right. Ethanol has this whole little non-polar area over here. Why is this area non-polar? Because the carbon and the hydrogen have similar electronegativities. It's also symmetrical. You get that tetrahedral arrangement around this carbon. This, although it looks like this is 90 degrees, what's that actual bond angle there? 109.5, because we have that little tetrahedral structure there. Okay, so it is symmetrical. There's no positive and no negative ends. This is a non-polar area. So yeah, the ethanol has a slacker area which only has London dispersion forces, whereas water is all H bonding all the time. It's a tiny little molecule, so it can get very close to itself. And so water will have the strongest intermolecular forces. So where could we write that little thing here? We could write it down at the bottom. So in terms of IMFs, intermolecular forces, I'm writing this down because we have a new student with us today. Is it Raylan? Raylan? Okay, so Raylan is with us today and is learning some of this stuff for, the first time, so I'm gonna define a few extra words, but you guys get a good review in the meantime. So in terms of IMFs, propanol is the weakest. And then we have ethanol, and then we have water. And if that is the case, which one of those will evaporate the fastest? Propanol. Okay, so propanol is going to evaporate the fastest. Which one is going to and water will evaporate the slowest? Which one is going to have the highest vapor pressure? Propanone. Why did I write propanol? I meant propanone. It will have the highest vapor pressure. And water will have the lowest vapor pressure. So an AP exam type question could be, explain which one of these will have the highest vapor pressure or lowest vapor pressure based on, you know, properties of the molecules. And so you would talk about the intermolecular forces and the differences in their strength and why that leads water to have less vapor pressure. Is good? Okay. So that is that. Let's move on. Vapor pressure and boiling. A liquid will only boil when the vapor pressure of the liquid is equal to the atmospheric pressure. How can you get a liquid to boil? What's one thing you could do to that liquid to make it boil? You all know this one. You can heat it. And do you remember what they did last week on that little video we watched? You can decrease the yeah, you can decrease the pressure above the gas. Yeah. Yeah. Presumably. But it's really cold in space. But like, I mean, if you're out in space in like, say I presume, you know, the astronauts, they went up and they had to like have those frozen foods in water. I don't know. I honestly don't know. I don't know how it would work. I mean, you've got a blob of water floating there. It's not like it can be in a pan, you know what I mean, a pot or something, but yeah. Very strange, yes. Good question, but I do not know the answer. That'd be something fun to Google. I bet there's videos on it on YouTube somewhere. I would bet. Okay, increasing temperature causes more evaporation. The vapor pressure becomes strong enough to overcome the atmospheric pressure and liquid boils. Okay, that's what we talked about last week. Reducing the atmospheric pressure will also allow the liquid to boil. Again, we talked about that last week. Why does water have a higher boiling point on Long Island? We could say on Vancouver Island, make this more Canadian friendly, than in Banff. Bounce on a mountain. Yeah, it's up high. Up high. And what does that mean? The atmospheric pressure is lower. Okie dokie. Oh, look, there's an answer on the next page, so we didn't even have to write that. Excellent. Okay. Boiling point is the temperature at which the vapor pressure equals the external atmosphere. Normal boiling point. Do you remember what normal boiling point is? Yeah, it's the temperature at which the vapor pressure of the liquid equals 1 atmosphere. Substances with high boiling points have strong IMFs. So we could use that same logic from propanone, ethanol, water. Which one would have the highest boiling point? Water. Because it has the strongest IMFs. Okay. La la la. I feel like this sheet really needs like a lot of editing. I think I just kind of threw it together at the last minute. Boiling versus evaporation. Boiling occurs throughout the liquid, right? You get those bubbles forming. They can happen at the top, at the bottom, anywhere. It occurs at a definite temperature. It occurs at a constant temperature. If you heat water that is boiling, and it's at 100 degrees, if you keep heating it, and let's say you make the flame even hotter, what will happen to the temperature of the water while it's boiling? So I got some water that's boiling, and I've got a flame under it. And now I increase the temperature of the flame, and the water is still boiling. What's the temperature of the water? It's the same. As long as the water is boiling, it cannot be above 100 degrees Celsius. The extra energy goes into, instead of making the particles move faster, it goes into breaking the bonds and increasing the potential energy of the particles by separating them from one another. That's going to be part of the summer assignment, is looking at phase diagrams. So what will happen is, as you heat water, this is, what are we doing here? This is the temperature, and this is time, and we're heating the substance. If it's as a liquid, it'll start at, say room temperature, and the temperature will increase as we heat it, like on the stove or whatever. And then as it boils, the temperature will stay the same, because in here, the added heat causes the particles to move faster. So it increases the kinetic energy. But at some point, the particles are moving so fast that they will break apart from one another. And what kind of a process is bond breaking? Bond breaking is always endothermic. So as we continue to heat this substance, once we've gotten to 100 degrees, now if we have all the little water molecules, which are all stuck together like the paper clips in this cup, okay, you see the paper clips in the cup, they're like the little water molecules, and they're moving faster, and they're moving faster, and they're moving faster, and now and that is increasing kinetic energy. The next amount of energy that goes in, as soon as they're at 100 degrees and they're moving that fast, the next bit of energy that goes in causes the particles to separate from one another and increases the potential energy of this particle, because now this particle is on its own. We've broken that bond. So in this part of the curve, I know it's a curve, it's a straight line, but that's okay, we call it a curve. In this part of the curve, this is boiling. Okay, so this is a liquid. This is the liquid plus a gas. The temperature stays the same because the added energy breaks the bonds. That's a little preview of some of the summer assignment. So we have a liquid and a gas. Over there we have liquid. What do you think happens when the temperature starts rising again? What do you think has happened? it's all turned into gas. And if you continue to heat it, if you have in a container where you can, keep that gas being heated, the temperature of the gas will then rise. Okay, so that is it for today. I will see you guys next week.